Have you ever noticed that almost every ship in the world has a red bottom? Why not blue, white, or any other color like the rest of the hull? Why red? And it's not random. Every major shipping company on the planet, no matter their logo, their colors, their country, paints the underwater part of their ships the exact same shade of deep brick red. There's a reason for this, and by the end of this video, you'll know exactly why. Before we talk about paint, we need to talk about what the paint is fighting. The moment a ship enters the water, the clock starts ticking. Within minutes, a thin, invisible layer of proteins and dissolved organic matter coats the hull. Within hours, bacteria arrive. They eat the organic film and begin forming what's called a biofilm, a sticky, microscopic community glued to the hull. And once the biofilm is established, the party invitations go out to the whole ocean. Barnacles, tube worms, zebra mussels, bryozoans, algae, sea squirts. Collectively, this is called biofouling, and it is one of the most expensive problems in the entire shipping industry. Here's why it matters so much. Every organism that latches onto a hull increases drag. The ship has to push harder, burn more fuel, and move slower just to cut through the same water. Studies show that heavy biofouling can increase a ship's fuel consumption by up to 40%. For a large container ship burning hundreds of tons of fuel per day, that's a catastrophic cost. And fuel isn't the only issue. Biofouling also introduces invasive species to new ecosystems. A ship leaving a port in Japan and arriving in California can carry organisms on its hull that have never existed in those waters before. Some of these species have no natural predators in their new environment. They multiply. They devastate local marine life. Biofouling has been called one of the leading causes of marine biodiversity loss worldwide. So, how do you stop it? Humans have been fighting this battle for as long as we've sailed ships, and the solutions throughout history are equal parts ingenious and absolutely wild. The ancient Phoenicians, among the greatest sailors of the ancient world, coated their hulls with a mixture of tar and arsenic. Yes, arsenic, poison, rubbed onto the wood to discourage marine life from attaching. It worked reasonably well, and it set a pattern that would define anti-fouling technology for the next 3,000 years. If you want to stop sea creatures from living on your hull, you make the hull toxic. The ancient Greeks and Romans used lead sheathing, thin sheets of lead hammered directly onto the wooden planks below the waterline. Lead is poisonous to marine organisms and provides a physical barrier against boring worms that would drill into the wood. The Romans were essentially putting toxic metal armor on their warships. Fast forward to the age of sail, 17th and 18th centuries, and ships were now crossing oceans regularly. The problem was worse than ever. The Royal Navy tried copper sheathing in the mid-1700s, and it was a revolution. Copper is naturally toxic to barnacles and algae, and it's durable. British warships sheathed in copper were faster and required less maintenance than their rivals. Some naval historians argue that copper-bottomed ships gave Britain a significant strategic advantage during this era. But copper was expensive, and eventually, as ships transitioned from wood to iron and steel in the 19th century, it caused a new problem: galvanic corrosion. When copper contacts iron in seawater, which acts as an electrolyte, an electrochemical reaction occurs that corrodes the iron hull at an accelerated rate. The very thing protecting the hull from barnacles was eating through the hull itself. Engineers needed something new. In the mid-1800s, a new class of product emerged: anti-fouling paint. These were paints mixed with toxic compounds that would slowly leach into the water right at the hull surface, creating a permanently hostile environment for any organism that tried to attach. The key ingredient? Cuprous oxide, a compound of copper and oxygen. And cuprous oxide is red, not a dark, subtle red, a bold, brick red, the kind of red you can spot from a mile away when a ship is in dry dock or riding high in the water. This wasn't a design choice. Nobody sat down and decided ships should have red bottoms for aesthetic reasons. The color is simply a byproduct of the chemistry. Cuprous oxide happens to be an excellent biocide. It kills barnacles, algae, and worms, and it happens to be the color of dried blood. The paint works through a process called controlled leaching. As water flows over the hull, it slowly dissolves the surface layer of paint, releasing tiny amounts of copper ions. Copper is toxic to marine organisms at even very low concentrations. It disrupts their metabolism, prevents larvae from settling, and kills biofilm-forming bacteria before they can get established. The paint essentially creates a perpetual, slow-release poison barrier around the entire submerged surface of the ship. But here's what makes it clever from an engineering standpoint. The paint is designed to erode at a precise, calculated rate. Too slow, and the copper stops leaching, and the biofouling takes hold. Too fast, and the paint disappears before the next scheduled dry dock maintenance. Naval engineers spent decades perfecting the formula, so the paint erodes at exactly the right speed to keep a hull clean for the optimal period between maintenance cycles. Now, and this is the part most people never talk about, anti-fouling paint has a complicated history. For most of the 20th century, the dominant anti-fouling agent wasn't copper. It was something far more effective and far more dangerous: tributyl, or TBT. TBT-based paints were introduced in the 1960s and were extraordinarily effective at preventing biofouling. But by the 1980s, scientists noticed something alarming near busy shipping ports. Oyster populations were collapsing. Female dog whelk snails were developing male reproductive organs. Entire coastal ecosystems were showing signs of severe endocrine disruption. The culprit was TBT leaching from ship hulls into the water in concentrations that were toxic not just to barnacles, but to everything. TBT was so persistent in marine sediments that it continued causing harm decades after it was applied. In 2008, the International Maritime Organization banned TBT-based anti-fouling paints worldwide. It was one of the most significant environmental victories in maritime history. The industry shifted back to copper-based paints, which are far less persistent in the environment, and research exploded into new alternatives: foul-release coatings that are so hydrodynamically smooth that organisms can't grip onto them, silicone-based paints, and even experimental biomimetic surfaces. Hull coatings inspired by shark skin, which has microscopic riblets that prevent biological attachment. But for now, on most commercial ships around the world, the bottom is still red, cuprous oxide. Same basic chemistry as 150 years ago. So the next time you see a massive container ship or tanker riding low in the harbor and you catch a glimpse of that distinctive red below the waterline, now you know the whole story. That color is the result of thousands of years of human ingenuity. Ancient Phoenicians with their arsenic tar, Roman legions hammering lead onto warships, Victorian engineers discovering copper, a global chemical crisis caused by a paint that worked too well. The bottom of a ship is red because the ocean is relentless, and humans, in their way, are even more relentless. If you found this interesting, hit subscribe. We cover the hidden science and engineering behind the things you see every day but never think to question. And drop a comment below. What's a common thing you've always wondered about? Your question might become the next video. See you next time.